This lecture is going to talk about functions in programming languages, but specifically, of course, in languages like Java and C++ and the languages we're familiar with. When we think about functions, what we're really thinking about is subprograms, little isolated fragments of code that have, some sequence of lines of code that get executed, and that subprogram, that sequence of code, gets packaged up, wrapped up in curly braces and given a name. And you invoke that subprogram by giving its name, and you perhaps give arguments to that subprogram. So you will call these subprograms functions, or you'll call them subroutines, or you'll call them methods, depending on the language and the context, but all those things kind of mean the same thing. The important thing to understand here is that these subprograms, the subprogram abstraction, provides two different kinds of capabilities. It provides a process abstraction, that is to say, something or other having to do with code that gets executed. That's a process abstraction, isolating off some code that gets executed. And then there's the idea of data abstraction, that executing code is somehow associated with some kind of format, functionality that you want to provide on the data. So let's get right into it, right? Important fundamental aspects of subprograms. Each subprogram has a single entry point, one starting place. When you call a subprogram, when a program calls a function, that program stops everything while the subprogram is executing. So when you call a function, your program stops because the function is running. And you don't start up again until the function, the subprogram terminates, until the function that you call is done. So you run your program. When you invoke some subprogram, you stop so that that subprogram can run. You sit and wait for that subprogram to be finished. And when it's finished, you pick up where you left off. So only one function can be running at any given time. And because there is this interaction between the called function that has to know to stop and has to know somehow to pick up where it left off when the function is done, calling a function is an interaction between the caller of the function and the function itself. When you define a subprogram, you define the interface to the subprogram, that is to say, its name and everything that goes into it and everything that comes out of it, and the actual body of the subprogram itself, the actual code that gets executed when the subprogram gets invoked. We invoke a subprogram by calling the subprogram, or we make a function call, or we make a method call. That means that you want the subprogram to be executed. And remember, if you want the subprogram to be executed, you stop, let it execute, wait for it to be done, and then pick up where you left off after it's done. The only thing you, from the outside looking in, know about a subprogram is the subprogram header, the name of the function, the kind of function it is, what it might return, and the parameters that go into the function. Okay, and we call that the subprogram header. We call the arguments to the function, the number of arguments, the order in which they have to appear, and the types for those arguments or those parameters. We call that the parameter profile. And the protocol is the parameter profile and a return type. So the protocol for a function is the arguments that it takes and whatever it returns. So you know that a particular function, if it takes 2 integers and returns an integer, you know that. That's the protocol for accessing that subprogram. And frankly, as a programmer, using that subprogram, that's all you need to know, and that's all you do know. Now, those declarations of those profiles there, they're sometimes called prototypes, okay? You declare a prototype for a function that tells you, or that tells the compiler, what the name of the function is, what the parameter profile is, what the arguments are, and what order they're supposed to be in, and what the types are, and what the return type is. That prototype tells you everything you need to know in order to call that function. When functions take arguments, we say that those arguments are the formal parameters to the function. So if I say, some function named f that takes a parameter int x and int y, x and y are the formal parameters, the dummy variable names that are used inside the subprogram. When you call a function, though, you're not giving it x and y, you're giving it some values for the parameters. Those are the actual parameters. So when you call a function, you give the function actual parameters, you pass parameters into the function, and those actual parameters are bound to the formal parameters inside the function itself. Now, how that's done depends upon the language. Just about everybody uses a form of argument binding or parameter binding called positional parameters. So the binding of actual parameters to formal parameters is by position. If I declare that a function takes 2 arguments, and the first argument is an int and the second argument is a float, then the first actual parameter that I pass gets bound to the first formal parameter. And so it better be an int. And the second value that I pass, the second actual parameter, gets bound to the second formal parameter. And again, it better be a float. The types better match. Some languages support something called keyword parameters, where instead of knowing the argument by its position and type, there's a keyword. So, you might have a function that takes 2 parameters, x and y, and if you want to pass x and y in, you call the function by saying, function x is this value and y is that value. So you explicitly lay out what the binding is between the actual value and the formal parameter. The formal parameters are the keywords, and the actual parameters are the values. So some languages provide passing arguments by keyword value pairs. Many don't. Most of the languages we're used to write are positional. C and C++ and Java are all positional. As we've discussed before, some languages provide default values. Default values are just values that are provided for parameters when a actual value is not passed to the function. And they have to be positional. They have to be at the end rather than at the beginning. Some languages support the ability to pass a variable number of parameters, right? And there's all sorts of odd ways that this is implemented in languages like C and C++. A lot of the idea of passing a variable number of parameters involves some mechanism of somehow figuring out how many parameters are passed in a variable parameter list, and geez, what are the types? There has to be some mechanism of figuring out what the types are. The old style C programming language printf function declaration, where you pass it a string that has a bunch of formatting characters in it, is a way of managing the types and number of actual parameters that are passed in a function that supposedly takes variable numbers of parameters. Languages like C# and Ruby and Python have their own ways of providing for variable numbers of parameters in a way that's a little safer. Now, you may find a distinction drawn in some languages between procedures and functions. The Fortran programming language draws a distinction between a subroutine and a function. So that would be a procedure, a subroutine, collection of statements that do something but that don't return any value. And a function, similar to a procedure, does some calculations but returns a value. Now, it turns out that in some languages, functions are pure in the sort of an abstract sense. They produce no side effects. But in practice, functions have side effects. They change values of various things. They change global memory, etc. So in a language that allows side effects, the difference between procedures and functions is small. And in fact, you could make the argument that the only difference between a procedure and a function in some of our languages is, well, something that doesn't return anything, some function that is declared to be void, so it doesn't return anything. Well, that's a procedure. But anything else that returns any kind of value, a function that returns an int or a float or a pointer, that's a function because it's doing some calculation and it's returning some value. But this is a distinction that matters a great deal in certain kind of functional programming languages where there are no side effects, or in Fortran, for example, where there's a separate calling of a subroutine and invoking of a function. But in languages like Java and C, there's not a big distinction between these two things. If you think of a function that returns void, that is to say, returns nothing, well, you could call that a procedure and you could call everything else a function, but it's not that big a difference. When languages provide subprograms, there's a bunch of questions that have to be answered. Can those subprograms have local variables, and are those local variables static or dynamic? Can we have subprogram definitions inside of other subprogram definitions? Can function definitions be nested? How do we pass parameters? Do we check the types of parameters? Do we check the values? Do we check the number of parameters? Can we pass functions as parameters? Can we overload subprograms? Can we make them generic? Do we support closures? We'll talk about what all those things are. Now, people who implement these things can decide to either make, in most contemporary languages, locals or stack dynamic. You can, if you want to, on a one-off basis, decide that you want a particular variable to not be dynamically allocated on the stack, but to rather be static and always in the data area. And we do that by declaring an individual variable as static. So that's local variables. Now, how do we pass parameters into functions? Well, from a semantic basis, there's really only a couple things you can do. We can say that we pass parameters to a function in mode. You copy a parameter into the function at the beginning, or you can say that we have something called out mode, where you copy a parameter out of the function when it completes. Or you can say in-out mode, doing both. Now, in concept, this is true all over the place, but in practice, the way it actually is implemented in C and C++ and Java is a good bit simpler. What we do is we copy values into the function almost all the time, okay? When I pass a parameter to a function, I am copying the value of that parameter into the function. I am, in essence, initializing the formal parameter to the value of the actual parameter by making a copy of the value. When I say f of 3, I'm copying the value 3 into the function. When I say f of x, I go and I get x's value, and I copy that value into the function. Now, if a function takes a pointer, if one of the arguments is a pointer or one of the arguments is a reference, then that means that I am giving the function an access path to the variable. If a function takes a pointer to an integer, I have to initialize that pointer to point at some integer. If I have a function that takes a reference to an integer, I have to initialize that reference to refer to some integer from the caller. So it's again copying a value in. The concept is the same. I copy the value in, but I might be copying not the value, but the reference to a value. But whether I'm copying the value or whether I'm copying a reference to the value, I am copying something in. And programming languages that support this, we say that these programming languages support pass by value or call by value. And that's the way C and C++ and Java works. The value of the actual parameter is copied into whatever memory space the formal parameter is using, and away you go. So that means each function has a copy of the arguments. So there's a couple things, right? There's a cost associated with that, right? You know, I'm copying a value in, so that value's in two places, right? I have an integer in the caller, and I pass it down into the called, so I'm copying that integer. That copying takes time. Yeah, maybe not a lot, but it does take time. It also takes space. The integer in the function is a separate discrete integer from the integer in the caller. So there's twice as much memory needed. The other thing is that if I pass a pointer into a function, if the argument to a function is a pointer or a reference, then accessing the value costs more. Indirect addressing. That's true in all cases, right? Every time you're accessing something by way of a pointer or a reference, it takes a little bit longer because you have to dereference the pointer. So if you think about it, right, if I'm copying values into a function and the thing that I'm copying is huge, it's probably smarter for me to copy a reference to that big thing rather than the thing itself, because the amount of memory needed for the reference is almost certainly smaller. I might be nervous about copying a memory address into a function, because if I copy a memory address into a function, that function can dereference that memory address and do whatever it wants with it, and that's a problem maybe. In cases where I want to make sure that the function can have access to memory, but can't make changes to memory, I can declare a particular parameter to be const. If I declare a parameter is const, then that means that the function gets a copy, but the function can't change the copy. And that's sometimes useful. Languages support out mode, right? Pass by result. Most of the time when you think about pass by result or out mode or what comes out of the function, you should think about the return keyword in the language. When I return something, when I say return X, I am copying a value out of the function back into the caller, right? So calling a parameter passing a parameter to a function in in mode makes a copy in, return makes a copy out. And we say that the function returns an int. That means that an int is what's going to get copied out. We say that a function returns a float. A float is what's going to get copied out. If it's a big object, the big object is going to get copied out. And again, that might not be efficient. So maybe if we've got big objects that we're manipulating, we want to copy not big objects, but references to big objects or pointers to big objects. Now, there are some languages which, instead of doing explicit returns of a single value, they just declare that certain parameters can be out mode parameters, which means that at the end of the function, all of the actual values for those formal parameters get copied out. This tends to cause problems and messes, right? And you can see that illustrated here on this slide. If I have a function that has out mode parameters and I say sub P1 comma P1, so I'm copying values in. The value of P1 is what the first formal parameter is set to, and the value of P1 is also what the second formal parameter is set to. When the function's done, there's some value in the first formal parameter that gets copied into P1, and there's some other value that's in the second formal parameter that gets copied into P1. Well, which value gets copied when? Which one gets copied first? Blah, blah, blah. That's a problem. So generally, this can be avoided by, well, it can be avoided because we don't really run across this in any of the languages that we usually use. The only way to get something out of a function in these languages is to return something. Now, pointers and references, when used as parameters, allow you to, well, it helps you create side effects, allows you to move things back and forth more easily into and out of the function. So if a parameter is a reference, it's automatically initialized to refer to the variable in the caller when the function is called. So if I have a function whose first argument is a reference to an int, and I pass it an int, the reference is automatically initialized in the function to refer to the int that I passed. This always works this way in Java. References are copied around instead of the actual objects. In C++, a reference to a type is initialized to refer to the particular type that's passed to the function, and that's great. Now, when you declare a parameter to be a const, that means that the function is not allowed to refer to change what the reference refers to. So if I say that a particular function takes as a parameter a const int, a reference to a const int, you can dereference that reference and see the integer, but you can't change it. So that leaves us with this point here. You can pass a non-const value to a function that takes a const parameter, but you cannot pass a const value to a function that takes a non-const parameter. Let's break that down. In the first case, I have a value that's not a const. I give it to a function that takes a const parameter. Well, that's okay. The fact that the function isn't going to make a change to that, to what the reference refers to, it doesn't matter that much. However, in the opposite case, I have something that's a const, and I pass it to a function that takes a non-const parameter. That's a problem. I have a variable that's a const, and that means that that variable, I don't want that variable to ever change. If I initialize a non-const reference, that means that function might change that variable, but I've declared that variable const, which means I don't want to change it. So if I have a const object and I try and pass that const object into a function that takes a non-const reference, it won't compile. Okay. Similar with to references is pointers. If a parameter is a pointer, the argument must be a pointer or the address of the variable of a proper type. And constness can work with pointers too. It's a little more complicated. We'll get to that in a later lecture. But in both cases, the function has access to either the pointer or the reference, and it can dereference the pointer or dereference the reference and get access to what the thing refers to. That means that you can be efficient. Instead of passing big giant objects around, you can just pass around smaller smaller pointers to objects. But it does make it possible that there might be side effects, that your function might dereference the pointer or dereference the reference and make a change to a variable and do something to some other variable in the program other than what gets returned by the function. Okay, so great. This all works. It actually works by communication through the stack. Okay, the runtime stack is the mechanism that's used to pass arguments into functions, to have local variables in functions, and to return values back from functions. Okay. C does pass by value. You can copy pointer values around, and that achieves a sort of a pass by reference. C++ has pass by value, it has pointers, and it has pass by reference. The value of the reference is copied. Java automatically passes basic types by value and passes objects by reference. C# has pass by value, and if you want to use pass by reference, you have to precede the formal parameter with the keyword ref. Other languages have different ways of handling this sort of stuff. PHP works the same as C#, except either parameter can specify ref. Perl places all actual parameters in a predefined array named @_, which is, I don't know, it's a terrible naming convention, and it's completely unreadable, but there you are. Python and Ruby use pass by assignment. Actual is assigned to the formal when you call a function. And the more modern the language, the more likely is that there's type checking. Fortran 77 in the original C had no type checking, but everybody else does type checking, pretty much, right? Java, C++, more recent dialects of C. We type check the parameters. We make sure that the count of parameters matches, the types of parameters match, the types of return types match, and we make sure that we use that name mangling stuff that I mentioned in an earlier lecture to call the actual proper function. Some languages don't require type checking, and in some languages, type checking isn't even possible. You can You can't explicitly declare in a Python function that a particular argument must be of a particular type. If it's important to you that an argument to a function be, say, a dictionary, you have to explicitly write code to check to make sure it's a dictionary. There's another small complication having to do with arrays. Okay. If multidimensional arrays are passed to a subprogram, the compiler needs to know the declared size of the array to build that storage mapping function, right? So remember when we talked about arrays and the way the array type is actually implemented, you have to know, for a two-dimensional array, you have to know how big each row is. So you index into a row, that means you have to know how big the row is, so you know how many integers to skip or floats to skip or whatever, right? So when you pass multidimensional arrays, you have to tell the program, you have to tell the function, a lot of information about the multidimensional array. You basically have to tell it the size of all of the higher level dimensions or higher order dimensions of a multidimensional array. You have to do that because the compiler has to know, how big the rows are or how big the other higher level dimensions are, so that when you index into this multidimensional array, it knows how much to skip. Okay, and that's all fine. It does mean that functions are a little bit less flexible. If you want to be passing around multidimensional arrays and the size of the arrays might be, the size of different dimensions might be different, it's probably a good idea to handle it a little differently, right? To put the big array into a class somehow and build the mapping function yourself. And frankly, if you're trying to build functions that take multidimensional arrays and there's lots of different possible multiple dimensions, that code ends up pretty complicated, and it's probably better to encapsulate it in a class anyway. Multidimensional arrays are easier in Java and C# and things like that, right? Arrays are objects, right? The arrays are single dimensioned and they're objects, and the object knows how big it is, so you don't have to worry about passing the size around. By passing a reference to the object, the function can take the array that comes in and look at its length member to see how big the array is. And multidimensional arrays are just arrays of arrays. So it's fine. The ith entry in a particular array is itself an array, and so it has a length member, and you know how big that dimension is too. So it's a problem that doesn't really exist in Java. Okay. So here's the thing: when you pass parameters into functions, right? There's a bunch of considerations about, some of these considerations are really sort of aesthetic considerations. What's the best and most efficient way to write, to deal with functions, to deal with code that's encapsulated, right? You probably want to give a function as little information as possible. Give a function only the information that it needs. So don't pass a function 15 parameters if it really only needs 1 or 2. And you want to minimize side effects. Side effects are useful in certain places and important in certain places, but sometimes they're a problem. And so you probably want to figure out a way to minimize side effects as much as possible. Pass things one way as much as possible. Use things like const or final so that whatever you're copying in, you're guaranteeing that the function is not going to have write access to those variables, isn't going to be able to change things, so that minimizes the side effects. Generally speaking, if you're passing around big objects, the message is really don't pass around big objects, pass around references to objects. It's easier, it's smaller, it's more efficient. And if you pass around references to objects and you mark those references as const references, then you can be sure that you are using memory as efficiently as possible and not exposing yourself to problems that might happen if you inadvertently make a change to something you have a reference to. So const or final is your friend. Now, so far we've really only talked about the basic things, right? Ints and floats and chars, and we've talked about classes and references to classes. And so you can have pointers to basic types, pointers to classes, and references to basic types and references to classes. And what about subprograms themselves? Is it useful to pass pointers to functions around? Well, the answer is, yeah, it actually can be useful sometimes. And if you do that, you need to figure out type checking for those function parameters, and you need to figure out if you're allowed to call that function. What's the proper referencing environment for a subprogram? The business of passing programs around or call. Now, other languages have different ways of handling this, right? C# does a nice thing called a delegate, right? A pointer to a method is actually implemented as an object called a delegate, right? So here we say that change is a delegate, sort of a pointer to a function. It can be instantiated with any method that takes an int parameter and returns an int value, right? And you can initialize it any way you want to. Delegates can store more than one address, which is called a multitask delegate. C# does this a little differently, and this delegate concept is actually a pretty clever and useful idea. Most of these languages support overloading. When we talk about overloading subprograms, what we're doing is drawing a distinction between different versions of the same function name based upon what their argument signatures are, right? Every overloaded subprogram has a unique protocol, right? A unique argument that is passed, argument sequence that is passed to it. So I can have a function named f that takes an int, and another function named f that takes a char, and another function named f that takes a float. And those three subprograms are different. The proper one that is called is selected by the compiler at compile time based upon the types of the arguments. So if I have a function named f that takes an int, and I have a function named f that takes a float, and I have a function named f that takes a char star, and I call f with the actual parameter 3.7, the compiler will say, oh, that's a float, and here's a version of the function that takes a float, so that's the function I'll call. Now, what's interesting in C++ and Java is that the overloads are overloaded by parameter types and sequences and numbers. But you can't overload based upon return type. I can't have a function named f that takes an int and returns an int, and another function named f that takes an int and returns a char. It's just not allowed. Okay. Now, another useful capability that's built into these languages, function support in these languages, is described in the next slide. It's called generics. The idea behind generics is that we parameterize the method by type. So let me say that again, because it's sometimes confusing. You know, we have functions that are parameterized by type. A function takes an integer, or it takes a float, or it takes a character, but we're not doing that with generics. With generics, we're actually taking the entirety of the code and parameterizing the entirety of the code by type. So you take a function and you wrap it up in a declaration known as a template, which gives you the ability to change the way a function is written based on type. So when you see function declarations with angle brackets, that's the use of a generic function or a generic subprogram or a generic class in C++, right? And we've seen this with vectors, maps, and sets. The idea is that you know, you might have a method or you might have a class where every single thing about the class is identical except for the type of some variable in the class. The algorithm's the same, the storage management stuff is the same, it's just the type. So you create a generic declaration for this method or this class, parameterized by type. And when you use that method or you use that class, the compiler generates code automatically for you on use. So here's what it looks like in C++. Generic subprograms are preceded by some kind of a template clause that lists what the generic variables are, right? So they can be type names, templated by type name, and you give it some identifier. In this case, we're giving it T. They can be regular typed parameters. Here it's a template is the second example here. The template uses a type name T and the integer n, and you can even specify default values. An example will probably make this clear. Let's pretend that we want to have a max function. So what is the maximum between two values? It's either the first one or the second one. Right? And the algorithm here is the same, right? If first is greater than second, then return first, else return second. There's that question mark colon expression. The algorithm's the same. The only difference here is the type associated with first, second, and the return value. With a generic, we simply say, okay, here's this method, and it's parameterized by type, and whatever type you decide to use, well, that's the particular instance of the function that gets called. So in the usage example below, in the first line of code, we say max string. See, the template parameter is string. So that's going to cause the max function to be created with type equal to string. In the second one, we're going to have the max function be created where max is equal to int. So the first function checks to see which string, this or that, is maximum. And in the second case, check to see which int, 3 or 7, is maximum. So you specify the type there. Depending on the compiler, depending on what's going on, the compiler might be able to determine what the parameter is without actually requiring you to specify the type. So there may be circumstances where the template is the parameter inside the angle brackets is not required because the compiler can figure it out from context. Now Java has this too. there's some slight differences. In Java, the type names, the parameters in Java have to be classes. Okay? And in Java, as compared to C++, Java actually only creates the function once generically, and all type checking is done at runtime. There are various things that might be done to specify restrictions on the types in Java, which is some function that's not available in C++, and there are even wildcards available in Java. For example, here, I have a template similar to the way, a similar functionality to the way the template worked in C++. The difference is there is no template keyword here. And we specify a type name T. DoIt is a function that takes an array of T named list and returns a T. And it's invoked in the same way. The invocation looks the same in Java as it does in C++. There's the method name, there's the type name in angle brackets, and then there's the call. Java lets the generics have constraints associated with them. So in this example, it can be T, it can be a class named T, but T has to be a class that extends comparable. So you might say, here's a generic for any class at all. As long as the class extends comparable, I'm good. And that'll work. And the ability to have wildcard types. So this code declares a template where, or a generic where it's a collection of anything. Works for any collection class. And the question mark is a wildcard. So both C++ and Java have this ability to have generics. There's just some slightly different ways of slightly different restrictions and slightly different features, but when invoked, everything kind of looks the same. Okay, so functions, I get to decide interesting and useful feature inside of a lot of programming languages, which is known as a closure. A closure is a function that refers to variables that are defined in the context in which the function is declared, right? So a free variable is some identifier that's used but not defined by the closure. So think about it this way, right? We talked about scopes, and we talked about nested scopes, and we talked about how I got a block of code and a variable is not declared in that block of code, so I can't I don't know what it is, but I can search in the enclosing scope and I can get access to that variable. So imagine that inner block is a function. And imagine that function has access to variables and the values of variables that weren't necessarily defined inside the function scope. So the model of it is kind of like parameters, I guess, but you don't actually have to declare things as parameters. And in fact, a closure is a kind of a function, but it's got a very narrow, limited definition and a very narrow, limited scope. And it's very handy, right? So let me give you some examples of closures and show you what they mean and how they might be used, right? So here is a JavaScript example. I have a function called makeAdder. makeAdder returns a function. Why? and the function y returns x plus y. So if we look a little bit further down, I create a variable named add10, which is the function that adds 10 to its argument. And then I have another function called add5, which makes a function that adds 5 to its argument. So makeAdder of 10 calls makeAdder, makes a function which returns 10 plus whatever argument is passed to that function. MakeAdder of 5 makes a function which returns 5 plus y, whatever the argument is passed to that function. So you can see here that this JavaScript code calls add 10 to 20. When I add 10 to 20, I should get 30. When I add 5 to 20, I should get 25. The closure is that anonymous little internal function that's returned by makeAdder. C# supports these things. We have nested anonymous delegates, which are basically little anonymous closure functions, right? And you can see there, the syntax is a little bit different, but I can make something called add10, which is a function that takes an argument that adds 10 to the function or adds 5 to the function, whatever it happens to be. So you can see in both of these cases, the 10 and the 5 are somehow captured and remembered so that add10 knows it's an instance of makeAdder to which 10 was passed. So that 10 value is somehow captured. Now Java has closures as well, and they look like this. A parenthesized list of parameters, optional, followed by that little arrow notation, followed by a function body. Function body can be a single statement, or it can be a curly brace enclosed list of statements. And the closure has access to local variables. Now, Java has this thing called anonymous inner classes. And if you've come across this, these are interesting and a little complicated. An anonymous inner class is like a closure, but it's not really a closure, right? So if you take a look at this fragment of code here, there's a function called addWindowListener. And addWindowListener has to take as a parameter an instance of a class, because that class is then is used then to call methods and pass things in, right? So instead of declaring a separate class and passing an instance of that class into the function, I declare the class and create a new instance of it all in one shot. So you see the first argument, the only argument, to this addWindowListener function is this new window adapter, right? And what is a window adapter? Well, you see the curly braces there? That's the body of the class definition. So this is a single class definition which only exists within the scope of the single argument to that function. It's an anonymous inner class definition. You create your own method. When addWindowListener needs to process a window closing event, it calls the window closing method in that anonymous window adapter class that is created there, and that causes the program to exit. Another interesting example shows the use of anonymous inner classes and closures to do the same thing. So let's say we have a list of persons, right? This variable called personList, which is a list of person, and I want to sort it. So the idea of sorting, right, is applying some comparator algorithm, right? If I want to sort things, I need to be able to compare individual pairs of things. So generic sort routines say, here's a list of things I don't want to sort, and here's the routine to call to compare two things, right? So there needs to be some kind of a comparator function. In the first example, the comparator function is declared as a method in an anonymous inner class, right? I declare the anonymous inner class. I say new comparator person, and then the curly brace enclosed code there is the class definition. Inside that class definition is a method definition. There is a public integer function named compare. So when the sort method needs to do a comparison, it invokes the compare method inside that anonymous inner class. I do the same thing with a closure. Instead of giving it a anonymous inner class, I just write the code right there at the bottom of the slide. See? So I've got a closure. I've got a tiny little mini function. Takes two arguments, a person named P1 and a person named P2. And when you invoke that function, it executes that single line of code there. P1.getSurname.compareTo, P2 gets surname. No anonymous inner class needed. There's a tiny little fragment of code, which is a function, which is called as needed. And that closure gets access to certain variables in the class. C++ provides closures as well with a slightly different syntax, but the idea is the same. Okay? The idea is you have a square bracket enclosed capture list. More about that in a second. The parameters in parens, an arrow, or just a function body if need be. And you can see two examples of this. In the first example, I have a function called GT5 that returns true if the val passed to it is greater than 5. I have a vector of integers, and I call COUNTIF. COUNTIF is going to count the number of times in this collection that GT5 returns true. So there it is, right? GT5 true. COUNTIF starts at the beginning, goes until the end, calls GT5 on each entry in the vector. Or I can just create a closure. Say I can have square brackets. I can have a function that takes an integer x, and the body of the code is inside of curly braces there, return x greater than 5. Square brackets is the capture list. This is, a slightly more type-safe version of the stuff that Java does. When I have a closure in C++, I explicitly say what variables from the defining scope are captured into the function. What variables that were in scope when the closure was created need to be used as part of the function. Okay, let's start to get to how this actually is used in practice. How does subprogram linkage work? What is the procedure that's used to call a function? To call a function, get all the arguments in, let the function do its thing, and return a value back. All of that stuff is called the subprogram linkage. How do I call a function? I have to pass parameters into the function. I have to let the function allocate its local variables on the stack. I have to save the execution status of the calling program, because Remember, when I call a function, I stop. And so I have to know where to pick up when I left off. So calling a function means set up pass parameters in, set the function up so that it has all its variables, save your execution states so you know where to pick up when you left off, and then tell the function to go, transfer control to the function. When you return, what do? Well, if there are any out mode parameters or in out mode parameters, or in our context, if the function returns something, the value has to be returned. Those values have to be recovered. Things have to be copied out of the function. Stack dynamic local variables have to be unallocated. I remembered where I was when I called the function, and now I have to restore that status so I can pick up where I left off and go pick up where I left off. All that stuff is implemented in something called the subprogram linkage, and the mechanism is known as the activation record. Everything having to do with keeping track of arguments, keeping track of return values, keeping track of local variables in the function, keeping track of where you were, keeping track of where the caller was so that its status can be restored, et cetera, et cetera. All of that is called the activation record, right? Every time you call a function, you create an activation record. Every time you return from a function, you destroy an activation record. A series of function calls where A calls B, and then B calls C, and then C calls D, creates a stack of activation records. Okay? Now, the activation records, they live on the stack. And interestingly, they are shared by the caller and the called. Okay? So think about it. The caller of a function, because it has the prototype for the function, it knows the name of the function, and it knows the type of the parameters and the number of the parameters. So it knows things about what go into the function, and it knows the return type, so it knows what comes out of the function. So clearly, the caller begins to create the activation record and begins to populate it with parameters. But the caller doesn't know what variables are declared inside the function. So the called function has to manage that part of the activation record. So the caller starts building the activation record. The called function finishes building the activation record, executes its code, figures about copying return values out, and then undoes what it did. Okay? All of the variables, either arguments or return types or local variables declared inside the function, all live in the activation record and are positioned in the activation record in some way. If I could look at the activation record, it would look like this, right? There's some return address, there's some mechanism of linking one call to another, there's the parameters, and there's the local variables. Okay? The format of the activation record is static, but its size may be dynamic, right? I may have no parameters or lots of parameters, so that parameter section might be different sized. My function might have no local variables or 100 local variables, and so the local variable section might be of varying sizes. But, no matter the size of those sections, they're all the same. The dynamic link tells you where the top of the activation record of the caller is. So that helps you thread your way back up to the caller, right? So you You create an activation record when the function's called, create it on the runtime stack. The system updates and manages this and keeps track of where it currently is on the stack. This is either a stack pointer or an environment pointer. It points at the beginning of the current activation record, and all the parameters and all the local variables are actually relative to that environment pointer. So here's an example. I have a function named sub, which takes two arguments, a float and an int. And inside the function, I declare an array of 5 integers and a float. So you can see that the activation record is going to have the return address. It's going to have the dynamic link, which is the environment pointer for the caller. It's got the two parameters, total and part. And it's got the locals, the array of 5 lists from 0 to 4, and the sum. So the environment pointer is somehow pointing into this activation record. The first argument is always right past the dynamic link. The second argument is always right after the first argument. The first local variable is always right after the last parameter. So all of these things are relative to, positionally relative to the other things in memory, right? The parameters always come before the locals. The first parameter always comes before the second parameter. The first local always comes before the second local, right? So the caller creates the activation record, saves the execution status of the current program, right? So what's the next instruction that the current program was going to execute? Compute the parameters, copy them in, pass the return address, and tell the called function to go. Then inside the called function, save the old environment pointer as the dynamic link, create the new value, add local variables, and away you go. On the way out, unwind the parameters, copy the return value into the activation record if there's a return, restore the stack pointer, restore the execution status of the caller, and then let the caller run. So the caller is no longer suspended. It picks up where it left off. All the things that got created in the activation record have been uncreated by the return. And all that's left is the return value that somehow got copied out. So let me give you an example of how this might work, and we'll give you an example that doesn't use recursion. I have a function called fun1. Fun1 calls fun2. Fun2 calls fun3. Main calls fun1. Okay? So main calls fun1. So you can see the activation record instance, the ARI, for fun1 has a dynamic link which points to the top of the activation record for main. It's got parameters and locals. Then fun1 calls fun2. So you see the activation record for fun2 is at the top of the stack. The dynamic link in fun2's activation record points to the beginning of the activation record for its caller. And you've got your parameters and your locals. And then in the next line of code, you can see, in the next picture, you can see the activation record for fun3 is on the top of the stack. The dynamic link points to the beginning of the activation record for fun2, and his dynamic link points to the activation record for the beginning of fun1. It's a stack of activation records, and they're all threaded together. This threading together is called the dynamic chain or the call chain, right? Local variables are offset from the beginning of the activation record, and that's the local offset. The local offset of a local variable is known by the compiler at compile time. So whatever the value of the stack pointer is, wherever in memory a particular function is using the stack, the parameter is always at a fixed offset from the beginning of the stack pointer. And the second parameter is always at a fixed offset from the beginning of the stack pointer. And the local variables are always at a fixed offset from the beginning of the stack pointer. The compiler knows that and generates code as efficiently as possible. Now, it turns out we can do things recursively with exactly this same mechanism. So here, main calls factorial. And factorial, as you can see, calls itself. N factorial is n times n minus 1 factorial. So I've got a recursive definition of factorial here. So the activation record for a call to factorial is return address, the dynamic link, the n value, and some other value that's returned, right? So first call, in the upper left-hand corner there, main calls 3 factorial. 3 factorial calls 2 factorial, so you can see there's another activation record for the second call to factorial. There, its parameter is 2. The dynamic link in the second ARI for factorial points down to the first ARI for factorial. The dynamic link in first ARI points down to main. Factorial of 2 calls factorial of 1, and you can see on the right-hand side that now I've got 3 activation records stacked up. Okay, so you can see I've got an activation record for factorial of 1, stacked on top of an activation record for factorial of 2, stacked on top of an activation record for factorial of 3. Now it's time to return. Okay, so here on the upper left-hand side, you can see that the value of n factorial is 1. When I return, that value is returned by the function, so that functional value 1 is copied out. And then the next instance, that returned value is used to do some multiplication, and there's a new functional value. Then that value is returned, and that returned value is used in another calculation to generate a new functional value. So you can see, eventually, we determine that 3 factorial is 6. Now, 3 times 2 times 1 is 6. Now, some languages, I'm sorry about that, not a lot, but some languages use stack dynamic local variables and allow nested subprograms. That is to say, you can declare a function inside of another function. All variables that can be non-locally accessed reside in some activation record instance in the stack. So it's similar to the scoping stuff that we talked about earlier when we talked about variable scopes. You're still looking for things on the stack. You're just looking not on a symbol table stack of nested scopes, but in a actual activation record stack of variable calls. So this is different from closures, which can be used anywhere and which have to capture variables. Nested subprograms exist only in a particular place. A couple of more things to talk about to sort of close this out, right? Blocks, curly brace enclosed lists of code, are in essence their own scope, right? And because they're their own scope, you can declare a variable, and that variable exists only within the lifetime of the curly braces there, right? So that temp only exists inside that block of code. How's this actually implemented? Well, you could, if you wanted to, have each block